Well, welcome back, everyone. In the previous session, I was talking about different outcome measurements and the different numbers, the different scales we use to measure outcomes and how we summarize them depending on the properties of that scale. What I'd like to do today is focus on one particular type of outcome, a nominal outcome, and focus on one special type of a nominal outcome, a binary outcome, for which there are only two categories. And lots of epidemiology deals with outcomes that are binary, dichotomous in scale. Now, the examples include such things as having a disease versus not having a disease, being dead or being alive. Now, in some situations, those are the only possible outcomes. By definition, your outcome is binary in scale. You can either be dead or you can be alive. There's nothing in between. There's nothing that's halfway between dead or being alive, unless you believe in zombies or something like that. But other outcomes are not binary by definition, but are created to be binary. For example, blood pressure. Blood pressure is a continuous measurement. I can put a cusp on your arm, pump it up, listen to these muffling sounds, and measure your systolic blood pressure in millimeters of mercury. It's a continuous number. But often that continuous scale is collapsed to become a binary scale. Hypertension versus not hypertension. You say that if a person's blood pressure is 140 millimeters of mercury or higher, you have hypertension. If your blood pressure is less than 140, you don't have hypertension. That's a very simplified version of the original continuous outcome. But by collapsing the continuous outcome blood pressure into the dichotomous outcome, hypertension, we lose information. For example, what we're saying is if we have two people, one whose blood pressure is 141 and another person's blood pressure is 181. On the hypertension categorization scale, they both have hypertension. You're not making a distinction between two people, one which has a blood pressure of 141 and one which has a blood pressure of 181, even though most physicians would be much more concerned about the person whose blood pressure is 181. On the other hand, you have two people, one with a blood pressure of 141, the other one with a blood pressure of 139. The first person would be called hypertensive. The second person would be called not having hypertension, not hypertensive, even though their blood pressures are only 2 millimeters apart. So when you have a continuous outcome, like blood pressure, and you choose to collapse it into a binary outcome, there's a huge potential that you could lose information by grouping people into categories. And within categories, we might have people with dramatically different values on the original continuous scale. And between different categories, you might have people whose values are very similar. That's a potential problem of making a dichotomous variable out of a continuous variable. The same problem is true if you have an ordinal variable. How is your health? Excellent, very good, good, fair, or poor. You might collapse people into two categories. Better health versus worse health by taking people whose reported health is excellent, very good, or good, putting them into one category, calling it better health, and putting the people with fair health and poor health in the other category. Again, you are losing information because in one category you have mixtures of people, some saying excellent health, some saying very good health, some saying good health. So keep that in mind when you choose to create a binary version of either a continuous or an ordinal outcome variable. Well, if that's true, if we lose information, you might ask, why are we doing it? And the reason is epidemiologists are simple people. They like to report results in simple ways, reporting things like risks and risk ratios, things we're going to be talking about in a future sequence of lectures. So what is gained in simplicity often comes at a potential loss of information. The other reason we collapse continuous and ordinal outcomes into binary outcomes is because that's often how clinicians choose to treat people. There are typically guidelines that recommend treating a person in a certain way if their blood pressure is above some threshold, treating them otherwise if their blood pressure is below some threshold. So in medical practice, often continuous measurements are categorized for practice purposes. Well, let's suppose we have a binary outcome, either because it's binary by definition, dead or alive, or it's binary because we've defined it so, hypertension versus no hypertension. How are we going to capture, summarize that outcome in a group of people? What sorts of measurements options do we have? And remember from the previous session, the outcome options we had for nominal measurements were either reporting proportions or reporting odds. And that's what I'd like to talk about in this particular session. So let me give you an example of measuring a binary outcome using proportions and using odds. And the example I'm going to use is your Framingham Heart Study data set that you'll be using throughout this course. And in that study, there were 4,434 people who attended the 1956 Framingham Heart Study exam. Of those 4,434 people, there are 1,944 men and 2,490 women. How would you summarize the frequency, the density, the relative amount of males, men, in that particular data set? Now the problem is, if you just said there were 1,944 men and told me nothing else about the study, I wouldn't be able to interpret that as representing a study with a lot of men or very few men. If those 1,944 men were the only people in the study, then the result would be this is a study full of men. But on the other hand, if the study contained hundreds of thousands of people and only 1,944 of them were men, that would be a study made up of predominantly women, females. So what we need is a point of reference to describe how big that group of men are in this study. And we have 2 points of references. We could compare the 1,944 to the total number of people in the study and say what part of the total number of people in the study are made up of men. That's going to be a proportion. Alternatively, I could compare the 1,944 men, the total number of men, to essentially the total number of non-men, women, in the study, to compare the frequency of males versus females in the study to get an idea of how common, how large the group of men were in that study. Comparing men to women, a part of the study to the non-part, leads us to another measure of describing a binary outcome, which is an odds. And I'll talk both about proportions and odds using this in another example. So first, our first option is to report a measure of disease frequency, or in this case, a measure of sex, a measure of male sex in the study, by describing it as the number of males out of the total number of the study, total number of people in the study. We have 1,944 men in this study out of 4,434 people in the study. That means that 43% or 44% of everyone in the study is a male. That's a proportion, a part over a whole. That's one option, probably the most common option for reporting a binary outcome, a proportion. The alternative, option 2, is to compare the number of men to the number of women. The part of the study we're interested in, the men, to the part of the other part of the study, the non-men, the women. So there are 1,944 men, there are 2,490 women. 1944 divided by 2,490, 78%, is what we call the odds of being a male in this study. Both of these calculations are legitimate. Both of these calculations are valid for describing the frequency of falling into one category of in this case, a variable, a binary variable sex, or in general, any binary variable, including binary outcomes. We can either report the proportion of people who develop the outcome or the odds of developing the outcome if we're following people over time and measuring how many people develop an outcome versus how many people don't. Now, these two measures, proportions and odds, are related to one another. By definition, a proportion is a part over a whole. Values for proportions can range from as low as 0 to as high as 1. So if you have a study full of women, the proportion of men is 0. If you have a study only made up of men, the proportion of men in the study is 1, 100%. So a proportion can run from as low as 0 to as high as 1. On the other hand, in odds is the part not divided by the whole, but the part divided by the non-part. And odds can range from as low as 0 to as high as infinity. Meaning, for example, if you have a study just made up of women, the odds of being a male in that study would be the number of men, 0, divided by the number of women, whatever that number might be. 0 divided by that number would be 0. On the other hand, if you have a study made up of only males, the odds of being a male would be the number of men divided by the number of women, the non-part. There are no women, so we'd be dividing by 0. The odds of being a male would be some number divided by 0, and sometime in your past, some teacher told you never divide by 0. Bad things would happen to you. Your computer would blow up or something like that. Okay, don't divide by 0, divide by a very small number, as small as you can think of a number. Instead of dividing by 0, divide by 0.00000.1, a very tiny number. When you divide any number by 0.00000.1, you get a huge number. Essentially, the smaller the number, the larger the quotient would be, the more huge your result would be. You essentially approach infinity. So the scale for odds are different from the scales for proportions. They can run from as low as 0 to as high as any possible number. So now, it might sound like we're having two different ways to describe this binary outcome, or this binary characteristic, sex in this case, but these two characteristics are related. Mathematically, if I gave you the proportion, you could calculate the odds. If I gave you the odds, you could calculate the proportion. Odds are nothing more than the proportion divided by 1 minus the proportion. So if I told you that 20% of the people in my study were men, and I asked you to calculate what the odds of being a male in my study would be, you'd take the 20%, divide by 1 minus 20%, the non-part, that's 80%. 20% over 80% gives you an odds of 0.25. 0.25 is the value for odds that corresponds to 0.2 for a value for a proportion. Similarly, if I gave you the odds and you wanted to calculate the proportion, all you have to do is take the odds and divide by 1 plus the odds to get the corresponding value for the proportion. So if I told you that the odds of being a male in my study was 25%, the proportion of men would be nothing more than 25% divided by 1 plus 25%. That's 1.25. 20.25 divided by 1.25 gives me back that 0.2 I had for the proportion above. So odds and proportions are equivalently in terms of values mathematically because one can be derived from the other. One is no better than the other mathematically. They might have different values though, but they are related one-to-one by these formulas. So here is a table that shows the corresponding value for the odds for any value for a proportion. And the proportions run from as low as 1% in this first column on the far left here to as high as 99%. And what I've put in the second and fourth column are the corresponding value for their odds. And let's just look at this table to see the relationship between a value for a proportion and a value for an odds. The first thing we notice is when the proportion is very low, 1%, 2% are bolded on this slide. Notice the value for the odds to 2 decimal places is essentially the same value. They differ in the 3rd decimal or 4th decimal place. But the odds corresponding to a proportion of 1% is going to be 0.01 divided by 0.99. And 0.01 divided by 0.99 is 0.01 something after that. It's close to 0.01. So for small proportions, the corresponding value for the odds are going to be very similar to the values for the proportions. And they stay similar up until about 10%. But after the proportion starts increasing beyond 10%, the value for the odds not only increases, but differs. So notice, when the value for the proportion is 50%, the value for the odds is 50% divided by 50%, which is now 1.0. If the value for the proportion is 90%, the value for the corresponding odds are 90% divided by 10%, and 90 divided by 10 gives you an odds of 9. And in the extreme case, if I have proportions of 98 or 99, which are very similar values on the proportion scales, notice the corresponding value for their odds are very different. 49 is the value for the odds corresponding to a proportion of 98%. 99 is the value for the odds corresponding to a proportion of 99%. Now that's going to cause a problem for us in epidemiology. Suppose I was doing a study. I was measuring a binary outcome in 2 different populations, and I wanted to see if the outcome was more common in one population than another population. And let me give you 2 examples. In the first example, let's suppose the outcome I'm measuring is rare. It doesn't happen very often. It happens 2% of the time in one population and 1% of the time in the other population. If you were going to try to summarize how much more frequent the outcome is in one population than the other, you're going to be comparing 2 proportions, 2% versus 1%. If you took their ratios, divided the 2% by the 1%, the ratio of those 2 proportions gives me a value of 2.0. You'd say the outcome is twice as common in the first population with this proportion of outcomes 2% than it is in the second population where the proportion is only 1%. But now if I come along and measure the outcome not using proportions but using odds, what sort of a message am I going to be giving to people? Well, I'm going to take your proportion of 2% and turn it into an odds by dividing 2% by 98%. I get an odds of 0.0204. I'm going to take your 1% proportion in the other population, turn that into an odds, divide 1% by 99.99, I get an odds of 0.0101. Notice the value for the 2 odds. 0.0204 is different from the proportion, 0.02. Notice the value for the odds from the second population, 0.0101, is different from the proportion for that population, but only slightly different, only different in the 3rd or 4th decimal place. So if I come along and report how much more common the outcome is in one population than the other by not dividing their proportions, but by dividing the odds that I get from that proportion, I'm going to divide 0.0204 by 0.0101. I get an odds ratio of 2.02. And that's not much different than the proportion ratio I had of 2.0. So for a small, rare outcome, if you report the outcomes using proportions, and I report them using odds, and we're comparing 2 populations where their proportions are small, your ratio of proportions and my ratio of odds are almost the same. We give almost the same number to people. But now let's look at a different example where the outcome is common, very common. Let's suppose it happens 99% of the time in one population, 98% of the time in another population. And again, I want you to describe how more common it is in one population than the other by dividing the outcome proportion in one population by the outcome proportion in the other population. Divide 0.99 by 0.98, I get a ratio of the 2 proportions that's only slightly bigger than 1.01, saying that on a proportion scale, the amount of disease that exists in one population is just a little bit higher 1.01 times what it is in the other population. But now let's suppose I come along with the same data, but choose to report the outcomes using proportions. I take your proportion of 99 and turn it into an odds. By taking 0.99 and dividing by 0.01, I get an odds of 99. I take your proportion of 0.98 and turn it into an odds by dividing 0.98 by 0.02. I get an odds of 49. What's my ratio now of the odds? If I divide the 99 odds of having the outcome in one population by the 49 odds of having the outcome in the other population, notice my ratio of odds is a little bit bigger than 2. The odds of having the outcome in one population is twice as much as in the other population. That message, ratio of odds equals 2, sounds different than the message, ratio of proportions equals to 1. Does that mean one of these calculations is right and the other is wrong for this second study where the outcome is very common? No, both calculations are perfectly valid, perfectly correct. They both are describing how relative the outcome is in one population versus another, one using proportions, the other using odds. And the message I'm trying to drive home here is when the outcome is rare, ratios of proportions, ratios of odds give you similar results. But when the outcome is common, ratios of proportions, ratio of odds could give you different results that are both perfectly correct, perfectly valid for what they're representing. Ratios of proportions in one case, ratios of odds in another case. Now, why am I stressing that? Let me give you an example where that was an issue in a published study. This is a study published in the New England Journal a number of years ago, one of their tables that I use. The reference is cited on the bottom of the screen. Essentially, it was a study looking at whether physicians might treat people different depending whether they're treating a male versus a female, or treating a person who's white versus treating a person who's black. So the way the study was done is that the investigators developed a number of vignettes describing a typical patient with a certain number of symptoms. And the question the respondent, the doctor who was completing the survey, was asked to do, would you refer this patient to a specialist, say a cardiologist, to care for maybe what was suspected heart disease? And some doctors received a description of a study and where you had the signs and symptoms of that person listed, and that person was listed as being a male, and others received the same description, same signs and symptoms, except that the patient was described as being a female. And in both situations, they asked on a scale of 0 to 100%, what's your chances of you referring this patient to a specialist? So what we have in this table, in the first column here, I have a little red circle around it already, is describing essentially the chances of being referred to a specialist on average by these physicians if that patient was a male versus if that patient was a female. On average, the chances of being referred to a specialist if you were a male, and I'll just write it over here in a little bit, was 0.906. And if you were female, it was 0.847. Now those are proportions. They're likelihoods of being referred to a specialist. You could divide the 0.906 over the 0.847 to get a message of how relatively more frequent men are referred to specialists than women. In this table, what they decided to do was to compare not men to women, but women to men. If you divide the 0.847 by the 0.906, you'll get a ratio of the two proportions, which is listed over here, equal to 0.93. The chances of being referred to a specialist if you're a female, if you're a woman, is 93% of that if you were a male, using proportions. But then the same investigators repeated the calculation now using odds. They took the 0.906, which is a proportion, and turned it into an odds by essentially taking 0.906 and dividing it by 1 minus 0.906, which is 0.094, to get the odds of being referred to a specialist if you're a male. And that's this number 9.6 in this middle box here. They did the same thing for females. They took their proportions, 0.847, and divided by 1 minus that proportion, which is 0.153, to get the odds of being referred if you were female. And that's the number 5.5 that's listed in this table. Now if you take the ratio of those two odds of being referred to a specialist if you're a female, divided by the odds of being referred to a specialist if you're a male, you get an odds ratio of 0.6. So here are the results. If you're talking about proportions, risks of being referred to a specialist for a female versus a male, the ratio of those two proportions is 0.93. Females are being referred less often, but not dramatically less often. It's 93% of that of men. But if you're reporting odds, you're getting a different result. you're getting a result not near 0.93, but equal to 0.6. It sounds like a different answer. It is a different answer because we're talking about ratios of odds rather than ratios of proportions, ratios of risks. Now, the problem in this study was not with the authors who did the study. They labeled their results odds ratios, or they labeled their results risk ratios. What happened was the interpretation of those results when people read the studies. They looked at the 0.6 and said, wow, there's a big disadvantage. If you are a female, your likelihood of being referred to a specialist is only 60% of what it would have been if you were a male. That sounds like a huge disadvantage of being a female. And it is the right answer if you're talking about odds of being referred, but people were interpreting that as if it's the risk of being referred, and that's where the problem came into play. So, here are some questions for you. If you were doing this study, which result would you present to describe the relative frequency of being referred to a specialist for a female versus a male, for a woman versus a man? Would you choose to represent your outcome using proportions, and where 90% of the men were referred to a specialist versus 84.7% of the women? The ratio of those 0.93 describes essentially the risk, the chance of being referred to a specialist for a woman divided by the risk, the chance for a male being referred to a specialist. The conclusion you would reach is that the chances of being referred to a specialist for a woman is 93% of that of a male. Or would you rather use odds as your measure of outcome and say that the odds of being referred to a specialist for a male are 9.6, whereas the odds of being referred to a specialist for a female are 5.5. And the ratio, 5.5 divided by 9.6, says that the odds of being admitted or being referred to a specialist for a woman is only 60% of that for a male. Now, the important point here that I'm trying to stress is both of those conclusions are correct. They might sound differently, but they are correctly describing the relative frequency of referral for women versus males, one using proportions, risks, if you want, as your outcome measure, the other using odds. And the reason the results are different is because we're talking about a very common outcome in this situation. So either one is fine. The choice is up to you. The important thing is that you convey to your reader which results you're reporting. Is it a ratio of odds or is it a ratio of proportions? Because in this case, the numbers were different. The results looked different. Even though they were correct, they tended to give different sounding conclusions. So it's important to label your results as ratios or odds or ratios of proportions. Okay, the next time we come back, I'd like to talk about one type of an outcome measure, a proportion, and then talk about what influences the size of a proportion, the size of what we'll be talking about then, the size of a prevalence. So I'll see you next time.